So I split my talk into two parts. First part is geometric computing, which is talks about the beginnings of the field. I mean, what we did 20, 30 years ago. And then the second part is about determining real roots of real polynomials. This is recent work. This is something I have worked on in the last 5 years. How do I move forward? Okay. In the first part, I talk about our naive times. I talk about floating point arithmetic in geometry, computing, and numerical analysis. This is based on a joint paper. Sylvain was one of the authors, and he's in the audience. And then in the second part, I talk about isolating roots of real polynomials, and this is joint work with Michael Zagralov. And I will also talk about the implementation, which is due to Alexander Kobel, Fabrice Rouillet, and Michael Zagralov. So some examples of geometric computing. I hope the projector shows. This is an arrangement of algebraic curves. It's some curves defined by algebraic equations, and we have computed the intersections, the planar graph defined by these curves. Yeah? This is not just a drawing of these curves. I show you a planar graph. It shows all the intersections at the intersections. It shows you the order in which the curves intersect and so on. What does it say now? I have to press OK. Okay, and now? Okay, so this is another thing. It's a curve, a surface, an algebraic surface in 3 dimensions and a visualization of it. Again, it does not show you an image of the surface. It shows you the topology of the surface. Or here, the intersection of 4 solids, a basic operation in computational design. Now, here's a first warning. A warning, at least I was not aware of when I started implementing geometric algorithms. So a very simple problem. This you see 5 points in the plane, and you see their convex hull. All 5 points lie on the boundary of this convex hull. And depending on the definition, this convex hull has either 4 vertices, the 4 extreme points, or it has 5 vertices. For either definition, you can change the output by moving this point V slightly. If you think it has 4 vertices, then moving V outside, it will turn it into 5 vertices. If you think it has 5 vertices, moving inside will turn it into 4 vertices. And since we are interested in computing a combinatorial representation of the hull, which in particular means you need to list the vertices, we are computing here a function which is non-continuous in its input, yeah? Because it's either 4 vertices or 5 vertices, and by moving V slightly, you can switch between the 2 outputs, yeah? So we are computing a non-continuous function, yeah? Which sort of is an indication that it might be non-trivial to do this. Now, Computational Geometry, one of the first papers is by Franco Preparata on computing the convex hull in 3 dimensions. And in this paper, which appeared in Communications of the ACM in '77, there is a sentence: the computational model we shall refer to is that of a random access machine, RAM, with the only modification that real number arithmetic replaces integer arithmetic. I really like the word only in this sentence, yeah? With the only modification, yeah? I mean, it makes it sound like it's a small modification. And I'm not sure whether Franco meant it this way, but I mean, it sounds like...
No, it turned out not to be that.
Yeah, okay, but I mean, it's the natural model for computational geometry because the parameters, point coordinates, line coefficients, radii of circle are real values. Secondly, numerical analysis has used this model successfully for many years. So it seemed like an innocent definition. I think the most important is the last sentence. It was key to the progress, to the success of the field. Yeah? Because, I mean, it was key to the success because on this model we could build our algorithms, we could ignore issues, and this was very crucial for for the success of the field. So it was a bold definition, I think, but was a very, very successful one. Now, there's a problem. You can buy RAMs. I have one here. You have all ones in your, you have all in your pocket, yeah, but you cannot buy a real RAM. Computers have bounded length integers and floating point arithmetic in hardware, arbitrary precision arithmetic in software, but they do not offer and cannot offer real arithmetic because certain things are undecidable. So once you turn to real numbers. Yeah? So they do not and they cannot offer. So it was a bold definition, but also maybe one which causes difficulty later. Now, when the computational geometry community, I began to implement geometric algorithms, we used the following definition of real RAM, namely it's a RAM plus floating point arithmetic. Yeah, so this is how I started. And here is an example. This is a Voronoi diagram of line segments, which I asked the student to implement in the late 80s. We found a few examples on which this program would work. I repeat the sentence. We found a few examples on which this program would work. On most inputs it would crash. Nevertheless, we used it frequently in demos when politicians would visit us because it created such beautiful pictures. And we would not allow the politicians to choose their own inputs. They had to choose between certain inputs which we would give to them. And in fact, when we first in LEDA, none of the geometric programs worked at the beginning. They were all incorrect. And and the reason is that floating point arithmetic is an unsuitable substitute for real arithmetic in geometric computing. And what I want to do in the next 10 minutes or so, I want to give you an example. Because it's sort of a textbook example of what can go wrong if you use floating point arithmetic, which I think you should take home. It's like this example, if you take a textbook on numerical analysis, they frequently have on the first 10 pages, they can also show you what can go wrong when you use floating point arithmetic naively. And okay, so the orientation predicate is a basic predicate in geometric computing. You have 3 points, P, Q, and R. And they either lie on a common line, or they form PQ or a left turn, or they form a right turn. And so the orientation predicate outputs 0, +1, or -1. And analytically, if you take 3 points PQR, you write down the determinant where in the first row you have 1 followed by the x and the y coordinate of the point P, and the same for Q and R. This is the formula essentially for the area of the triangle determined by these 3 points. And you take the sign of this determinant, this is the orientation predicate. Yeah? The sign of the area of the triangle. And float orient is the result of evaluating this predicate in floating point arithmetic. It's very important that really, when we write geometric or design geometric algorithms, we typically design them in terms of geometric predicates, orientation and things like that, collinearity. And then we use arithmetic to implement these predicates. So what is this now? This is the geometry of float orient. So what do I do here? I have 3 points, P, Q, and R all lying on the diagonal. And I evaluate, how can I use a pointer here? I evaluate float orient where I modify the point P slightly. Namely, I add x times u and y times u, where x and y run between 0 and 255, and u is the floating point unit. So this here, what you see on the left here, is a 255 by 255 grid. And for each grid point, I show you the outcome of float orient as either blue, left turn, red, right turn, or yellow, meaning the 3 points lie on a straight line. Yeah, this is what float orient tells you, yeah? So this is the point P modified by x times and y times the floating point unit. Down here is the point 0.5, 0.5. And float orient tells you whenever you plug in one of the yellow points for P, you get 0 as the outcome. If you plug in one of the blue points, you get +1. If you plug in one of the red points, you get -1. And, first remember, what should you see? Yeah, what should you see? I mean, what do you hope to see? Yeah, what you hope to see is a yellow line and then 2 half spaces, right? A blue half space and a red half space. But that's not what you see, yeah? There are many points misclassified as collinear. There are even some points where you have a left turn, it's classified as a right turn. There are some things which are really a right turn, but they're classified as a left turn, and so on. So this is the geometry of float orient. Now let's see what it does to algorithms. So here is a very simple convex hull algorithm in the plane, sort of it's taught in the first lecture of computational geometry, I guess. You construct the hull incrementally. You start with 3 points. You kept generally you have the vertices of the current hull in clockwise order. A new point comes. You first check whether it's inside or outside. If it's outside, meaning it can see some of the hull vertices, hull edges. What does it mean to see a hull edge? It means you have, the hull is stored like this. You have a hull edge, and if the new point is a right turn, you can see it. Yeah? If it's a left turn, you cannot. The new vert can, yeah? So you determine whether you can see some. It can of course see a consecutive sequence of vertices and edges. Yeah? And then what you do is you also have the 2 tangent vertices. You delete all the vertices in between and you you add the new tangents. Yeah? Meaning you have the sequence of edges which can be seen. I mean, these are the vertices that can be seen. You delete the subsequence and you replace it by the new edge. This is an output of this algorithm. If you use the floating point implementation of Orient. So the point is, I mean, you might hope that what you get is an approximation of the convex hull, which is something which is maybe slightly wrong. No. You can get things which are completely wrong. Yeah, like this. Yeah, so this is the convex hull of 6 points. 2 of them. What has happened here? What has happened here? Let me show it to you in detail. So for the first 4 points, the algorithm constructs the convex hull. The first 4 points are P1, P2, P3, P4, beautifully. Then comes the 5th point. The 5th point really lies inside the convex hull. However, float orient says that the 5th point can see the edge P3, P4. And so the point P5 is inserted between P3 and P4. And then it really looks like this. You have a concave corner at P5, which is invisible to the naked eye. Yeah, if you look at it at the screen, you don't see it because P4 and P5 are very close together and P5 is only slightly inside the hull, so you don't see this concave corner. If you look at it, the output at the screen. Now comes the point P6, which is down here. And P6, yeah, P6 can clearly see this, yeah. But it can also float see the edge from P5 to P3, and it does not float see the edge from P5 to P4. Yeah, so I mean, first of all, there's a violation of the invariant of the algorithm here, because the invariant of the algorithm is that you see a consecutive set of edges. Yeah, but this sees an edge here, it doesn't see the next edge, and it sees the next, okay? So now, what could happen, because of course it's the logic of the algorithm that you see a consecutive set of edges, you see this edge up here, the edge connecting P5 and P3, so you say, yeah, that's where I insert the point P6. Yeah, so you insert P6 between P3 and P5, and you get this. Yeah? You get even a self-intersecting curve. You get something which is definitely not convex, which is definitely not an approximation of the convex hull. And in the paper, we have examples of things, many more things that can go wrong. This algorithm can go into an infinite loop, it can crash, everything can happen. So I said at the beginning, it is a model which was used by numerical analysts successfully for many years. So what is different? So I think numerical analysis mainly computes continuous functions. For example, the eigenvalues of a matrix, not the rank of a matrix. Yeah, the rank of a matrix is a non-continuous function of the input, and numerical analysis would never compute the rank of a matrix. We are to a large extent interested in non-continuous functions. And I once gave this talk in front of a numerical analysis audience, and it said, well, this problem is ill-posed, or at least ill-conditioned. Yeah? You shouldn't compute it. But I said, we want to compute this. Yeah, we want to compute this. We use arithmetic to make yes-no decisions. Does P lie on a particular line or not? Numerical analysts never test for zero. Yeah? And I think, and the algorithms of numerical, they are self-correcting. Many of them are iterations and they are self-correcting. Ours are not. So what is the solution, which was, I think, proposed by GIAP in '93? We should implement a real RAM to the extent needed. This is the basis for Seagull and also LEDA. For linear geometric objects, efficiency and reliability was achieved in the 90s, till around the turn of the century. This required to develop some theory and serious systems building, which we did in Seagull. And since, I would say, 2002, we are concerned with nonlinear objects, algebraic curves, and so on. This requires lots of new theory on the interface of computer algebra and numerical computing, and serious systems building, which we did in Seagull. And many important contributions came from Inria for this, here in Sophia Antipolis, but also in Paris and Nancy. So let me turn to the second part of my talk, which is more recent research, work I've done in the last 5 years. So it's an ancient problem, yeah, going back 200-300 years. So given a polynomial with real coefficients, I will refer to this as a real polynomial in the following, determined its real roots. That is, compute isolating intervals for its real roots. So here is a polynomial in the bottom. Where's my, yeah. So this has 5 real roots, and isolating intervals are shown in red. Yeah? An interval is isolating if it contains exactly one root. This is what we want to compute. Yeah? We have the polynomial, and we want to compute intervals, one for each root, and this interval should isolate the roots from all other roots. And just to remind you of a basic fact in algebra, a polynomial of degree n with integer coefficients has n complex roots. And for a real polynomial, so polynomials with real coefficients, the complex roots come in pairs. Yeah? So we have real roots and complex roots which come in pairs, and the pairs differ by the sign of the complex coordinate. Yeah, so this is the problem which we want to solve. The motivation is nonlinear computational geometry. Here is you see the arrangement of 4 algebraic curves of degree 6. And the way the algorithm for this arrangement computation works, it's basically a very simple, it's a plane sweep algorithm. And the basic primitive you need is to intersect two algebraic curves. Let's say you have two algebraic curves P and Q given by polynomial equations Pxy equal to 0 and Qxy equal to 0. There is a procedure called variable elimination or the resultant calculus. You can eliminate one of the variables and obtain a polynomial R, which is then the product of the degrees. And this polynomial R has the properties that it is the projections of the intersection. Its root are the projections of the intersections, the projections of the complex intersections. You compute the real roots of this polynomial, and then you analyze the situation at each of these real roots. And analyzing the situation at each of these real roots means you take one of these x's, you plug it into P and to Q, and you determine the zeros in the second variable, y. So in order to carry out this program, what you need as a primitive for the polynomials is you need to be able to isolate the roots. You need to be able to isolate the roots even of a polynomial where the coefficients are, I mean, even if you start with integer polynomials, the x's going to be algebraic numbers. Yeah? So for the polynomials, after you have plugged in one of the x's, the coefficients are going to be algebraic numbers. And you need to be able to isolate the roots of polynomials whose coefficients are algebraic numbers. Yeah? And that's the problem we're going to deal with. Yeah, we want an algorithm that works for polynomials with algebraic coefficients. I exaggerated a bit. Real coefficients is exact and handles easy cases fast. That's also important. Easy cases fast. What are easy cases? Easy cases are where roots are well separated, or far apart. That should be easy. If roots are close together, that maybe we have to work a bit harder. What is the state of the art? The state of the art is that there are very effective methods for computing all the complex roots of a polynomial. MP-solve is a widely used implementation. It is widely used, although it does not have a global convergence proof. And there are theoretical methods to Schönhage and Pan, which, I mean, nobody has ever implemented these algorithms because they are so complicated. Yeah? And Pan in this paper writes, and probably they will never be implemented because of the complexity. On the other hand, for the real roots, there are very simple algorithms, subdivision methods, and I explain it to you in a moment. Descartes' method in Sturm sequences, continued fractions. They are simple. The algorithm is 5 lines, essentially. The worst case, however, the worst case running time is much worse than Pan. But on simple instances, these algorithms are very, very fast. There are excellent implementations. For example, Fabrice Rouillet's implementation algorithm RS, which is the default solver in Maple. Continued fraction method is the default solver in Mathematica. And what I'm going to tell you today is I describe a variant of the Descartes method, which is simple, I mean, keeps the simplicity. It is competitive with Pan's algorithm in the worst case, in theory. And the implementation by Alexander, Fabrice, and Michael is competitive with any other method on simple instances and beats all other methods by far on difficult instances. Yeah? On simple instances, it has about the same running time as the previous best methods. And on difficult instances, it beats everything by much. And it has replaced Fabrice RS solver as the default solver in Maple. So how hard can it get? Maurice Mignot from Strasbourg, okay, he's a professor was a professor in Strasbourg. He gave an example of a polynomial where roots are very, very close together. So this is this polynomial, x to the n minus 2 times ax minus 1 squared, where a is an integer. This is a polynomial which has 3 real roots, at x equal to 0, it's negative. At x equal to infinity, it's positive. And in between, it has two real roots. Because at 1 over a, it's positive. And slightly to the left, it has a 0. And slightly to the right, it has a 0. How close are these zeros? These zeros are apart about a, this is this number a here, to the n divided by 2. So numerically, if a is 2 to the 10, so 1,000, if n is 20, so we have a polynomial of degree 20, then the distance of these two roots is about 1 over 2 to the 100. Yeah, so they're really very, very close together. If I use tau for log a, then the distances of the roots is about 2 to the minus degree times tau. Yeah, degree is 20, tau is 10, so 2 to the minus 100. And this is as worse as it can get. This is really a worst case example because there is a theorem which is not too hard to prove. Let sep of p be the smallest distance between any two roots of a polynomial, any real or complex, then the separation is at least 2 to the minus n tau. And for Mignot polynomials, this is also basically the upper bound. Yeah, so this n tau is really the sort of the complexity of the problem, how bad it can get, how close roots can be together. Now we come to Descartes' method, which goes back to Descartes. He proved the underlying theorem, and then the algorithm is due to Collins and Akritas in 76, and Lane and Riesenfeld rediscovered it in 81. And the algorithm is extremely simple. So here is Descartes' theorem. Descartes' theorem says, if you have a polynomial, where for simplicity we assume that the constant coefficient and the leading coefficient are non-zero. You go through the coefficient sequence and you count how often it switches from +1 to from positive to negative. Yeah, so if this is the coefficient sequence, -3, 0, -2, 2, -1, then as you go through, here you switch from negative to positive, and here you switch from positive to negative. So the number of sign changes in the coefficient sequence is 2. Yeah? Here you reach 0, this doesn't count. You really want to change from negative to positive. Yeah? So here the number of sign changes is 2. And then Descartes' theorem of rule of sign is the number of real zeros of p on the positive line is at most the number of sign changes in the coefficient sequence. And secondly, both numbers have the same parity. Yeah? So V of p minus the number of real zeros is an even number. So, I mean, it's the proof fits on half a page. Yeah, it's not too hard to prove, but okay. And you can also apply this not just to the positive real axis, you can apply it to any interval AB by making this transformation. Because this function here maps the positive real line to this interval. So you can also find out how many sign changes, you get an estimate on the number of zeros in an interval. Now in particular, what does this tell you? If the number of sign changes is 0, there is no root. This is obvious for the real line, right? If all the coefficients are positive, there is no 0. Yeah? If you have only one sign change, you have only one root. Yeah? If only one sign change, you have one root. If you have more than two, if you have 2 or more sign changes, you don't know. And there is a second part. This is also very important, which is slightly harder to prove. If you have an interval which is shorter than the separation divided by 4, then you're guaranteed that you have at most one sign change. Yeah, if you have an interval, You compute this polynomial here for this interval, then you have at most one sign change. Yeah? So that means if you have small enough intervals, then this test will tell you whether you have a root or not. Yeah? If you have 0, there is no root. If there is 1, there is one root. And just let me tell you where this comes from. This is a converge which was proved by Landau and Obreshko. If you look at these two circles, so if you have an interval from C to D, and you look at two circles where the center of the circle are points which see the endpoints of the interval under an angle of 120 degrees, if the union of these two circles contains at most one root, then you will see at most one sign change. Yeah? If the union of these circles contains 0 roots, you will see no sign change. If it contains one root, you will see one sign change. Yeah? So this, now the algorithm should be clear. Yeah? The algorithm is what you do in order to find out the intervals, the roots in an interval from C to D. You compute the number of sign changes for this interval. If it's 0, you return. If it's 1, you say, well, this interval is isolating. Otherwise, if it's more than 1, you take the midpoint. You find out whether the midpoint is a 0 of the polynomial. If so, you return the midpoint as an isolating interval, and you recurse on both subintervals. Now, how do you start? Well, it is well known that the interval from minus p to plus m, minus m to plus m, where m is chosen like this, the maximum of the quotient of any coefficient divided by the leading coefficient, that interval contains all real roots. And the algorithm is guaranteed to terminate because by this, once we are down to an interval which is small enough, we see only one sign change. Yeah? So simple algorithm, very simple. Yeah? 5 lines. Well, and what does it take to implement it? Well, there are maybe some non-trivial parts. You need to find out whether the polynomial is 0 here. And of course, because these intervals get tiny, you need to compute with a high precision. But other than that, the algorithm is trivial. Yeah, but in order you need, and maybe the tree gets very big. Yeah, because you're essentially constructing a tree here. This tree might get big. Yeah, so it's a simple algorithm, but whether it's efficient, it's not so clear. Oh, 5 minutes. Okay, 5 minutes, 5 minutes, 5 minutes. Then I will not tell you anything how we improved it, but I will come immediately to what the effect of the improvement is. So here is running times for the implementation by Alexander Kobel, Fabrice Rouet, and Michael Zagralov of the algorithm which Michael and I found for the Mignot polynomial. So the polynomial x to the n minus the a now is specified as 2 to the tau. And here are running times. So the degree of the polynomial runs here increases from 250 to 1600, and the tau is always 14. This is MP solve. This is the continued fraction method, which is part of Mathematica. This is an implementation of an older algorithm of mine, which is part of the system SAGE. This is Fabrice's old implementation of Descartes' method, and this is the new implementation. Yeah, and you see we beat the other algorithms by large amounts. You also see that the growth in running time is a function of n. Here, I mean, we always double n, and the running time is multiplied by 4. So the growth of the running time in n is quadratic. Of the previous method, it was n to the 5. That's why they explode. And down here, you see the dependency on n is fixed, and we grow tau. Yeah, I mean, the roots are really, really very, very close, yeah? Remember, the distance, the smallest distance to the roots is 2 to the n tau, yeah? So 100 times 100,000, so this is 10 to the 7. So 2 to the minus 10 to the 7. That's how close the roots are, and that's how far you have to shrink the intervals, how close they get. So yeah, so this really requires high precision computation. But still, the growth in the running time in tau is slightly more than linear, which accounts for the efficiency of high precision arithmetic, which is used which comes from GMP. Here are the running times for easy polynomials. Random coefficients, polynomials with random coefficients are easy. And there the most important thing is that the last two columns, that by adding all these bells and whistles to RS, made it only slightly slower on easy instances. On easy instances, the method is still as fast as it was before, but on hard instances, it really wins. Let me, I summarize. I'm not telling you anything. Yeah, so in the second part, I gave you an algorithm which isolates roots of polynomials, has a worst case complexity similar to Pan's. It has been implemented. It's very fast for difficult polynomials. It's equal complexity for simple cases. For bitstream coefficients, it still has to, so this is integer coefficients. For the real coefficients, it still has to be done. And it also has consequences for more complex computations. For example, the topology computation of a polynomial, of a curve defined by a polynomial. Again, we could reduce the dependency on the degree from something like n to the 10. It's now down to n to the 6. I close here. I thank you for your attention.
Thank you very much. It's nice to see this recent progress on these problems I've not been looking at for years. So it's very impressive, but you were very, say, optimistic. And I would like to ask, are there cases you cannot solve? And is exact computing and this kind of technique the one to adopt in each case?
It's the approach that I adopted in each case. I don't think it's the approach to adopt in every case. Now, we certainly have to think about approximations when this is appropriate, and whether we can compute approximations more simply. It's just, I've worked a little bit in this direction, but I found it, it very quickly gets too complicated for me. So I work mainly on the exact computation paradigm, but I agree. It's also important to see how far one can, and in a certain sense, we are computing approximately here because we are doing lots of numerical computation, and we make decisions on, we see how exact we have to compute in order to make exact decisions. Yeah, so it is the numerical part is approximate computation. But I agree, we should, look into approximations for many of these problems. I just don't know how, okay, I stop here.
Thanks.
Before I say nonsense.
Are there other questions for Kurt Mehlhorn?
I was just wondering if you could briefly just explain how you actually improved the algorithm, maybe quickly.
Okay, there are two main ideas. One idea is that if the polynomial, if you choose a midpoint where you should choose a midpoint where the polynomial has a large value, because that decreases the amount of precision that you need. And the way we do this, you can either choose the midpoint, the split point, randomly, or what we do is we take several candidate split points because evaluation at a polynomial at many points is not more complex than evaluating it at a single point, and then take the split point where the polynomial is approximately maximum. And this can be done by an approximate computation. This is one idea, choosing the split point. And then you can guarantee that the recursion depth, the size of the tree is not much larger than if you would compute exactly. That's one idea. And the second idea is that these trees look very funny, because at the end you find n roots. And these roots might be very close together. So that means these trees have long stretches of nodes where you split off one of the intervals and you immediately discard it because the number of sign changes is 0. Yeah? And so these trees have basically very long paths where nothing happens. Just you split, you have the interval and you immediately discard the other part. Then our idea was, what we could do here is, can't we use Newton's method? We have a large interval, a small subinterval which maybe contain, in Mignot's case, there is the large interval which contains all the roots. There is the small subinterval which contains the two roots, which are very close together. And normal bisection has linear convergence. Newton's method has quadratic convergence. So what we do is, we estimate how many roots are in the interval by doing a Newton step from here and a Newton step from here and finding out maybe how big this cluster is. And then we use Abbott's method. Abbott's method, it's a variant of Newton's method, which guarantees this which smoothly changes between linear convergence and quadratic convergence. To actually, and for example, for this Mignot polynomial, if you do it without our trick for the Newton, the tree has a size of 10,000, and we cut down the size of the tree to, I don't know, 37 or 38. Yeah, so we eliminate these long paths where nothing happens. That's basically the idea.